Hi everyone, I hope everybody is doing well. And today's lecture, of course we're continuing the weather series until exam 2. Today's lecture, of course, will be about atmospheric moisture and precipitation, right? So these are the key terms that we're going to discuss throughout the lecture. So there is the hydrological cycle. So mainly today's lecture will be focused on the hydrological cycle. But when we're talking about the hydrological cycle, there are important processes and more important concepts that I'll introduce you to, including specific humidity, different ways of how we measure the humidity, what humidity is, and what condensation nuclei is, why that's important, and different precipitation forming processes, including how condensation, the types of different types of condensation, right? The hydrological cycle is one of the most important cycles we have on this planet, right? So we're referring to the transfer of water among the different Earth spheres, right? And so when we're talking about the hydrological cycle, unlike the carbon cycle, we can say that we're at equilibrium. What does that mean? So we have the ocean as the primary source of the water vapor in the atmosphere, right? But it's actually, since unlike carbon, once it is released to the atmosphere, that it is difficult to remove it from the atmosphere. Water vapor is actually easily removed from the system via precipitation, right? So whatever that's removed from one source, which is in this case, when we're talking about the hydrological cycle, of course, primarily the ocean, it actually finds its way to its original source, right? So we have this continuous interaction of continuous exchange of water between the different spheres, right? But there is no net gain or net loss because it is continuously being supplied, right? And so while the carbon cycle, there is of course a net gain because the carbon we have in the atmosphere is not as easily removed unlike water vapor, right? So when we're talking about these different processes, right? So fundamentally, the hydrological cycle, as you can see here, involves change of state. That's a very important element of the hydrological cycle. What does that mean? So we have evaporation, as you can see here, of course, and we also have condensation, right? And one term here, what you see is saturation, is a very, very important concept. It refers to the maximum amount of water vapor that an air parcel can hold, right? So we're talking about saturation. Well, when we have evaporation, of course, we're going to also have saturation, right? We have, that is like the air parcel will try to hold as much of water vapor as it can, right? Once we're past that saturation state, what follows is condensation. That means the air parcel can't hold can't hold any more water vapor, and then what follows is condensation, right? So there are different indices to measure the water vapor content, right? Also, while like not exactly indices when we're talking about vapor pressure, but these are important concepts for humidity, right? So when we're talking about humidity, we're talking about, like I said in previous lecture, we're talking about the amount of water vapor that is available in the air, right? So remember, for instance, I'll show you here again in the next slides that like it's very humid here in Atlanta, for example, during summer season compared to winter season, right? Because there is the amount of water vapor that's available during the summer is considerably higher during the winter times, right? So And then that has also consequences because water vapor is an important greenhouse gas. So it actually, it feels like it is 120 degrees Celsius, 120 degree Fahrenheit here in Atlanta, even if temperatures typically fluctuate between high 80s and high 90s, right? So that's because water vapor is actually an important greenhouse gas. But coming to the point, there are important terms that I would like to introduce here. So vapor pressure is one. Like when we're talking about vapor pressure, so it's a different form of atmospheric pressure, right? But now we're talking about water vapor, the contribution of atmospheric pressure that is due to the water vapor that's available in the atmosphere, right? And then there is saturation vapor pressure, right? Whenever we're talking about saturation, we're talking about the maximum, right? The maximum vapor pressure that can exist, right? So when we're talking about the saturation here, in terms of saturation here, not vapor pressure, but saturation in general, we're talking about the maximum amount of water vapor that an air parcel can hold, right? So, and then of course, we can measure humidity in absolute terms, that's specific humidity. That is actually now, we are actually quantifying the mass, the exact amount of water vapor that's present in the air. And this is usually expressed in terms of gram per kilogram. And then, of course, there is also, again, a term here, a term you see here, saturation specific humidity. Now we are actually talking about the maximum amount of water vapor that can be present, right? So while when we're talking about relative humidity, if you can recall from the previous lecture, it's actually expressed in terms of percentages, because relative humidity is actually a comparison. It's dependent on the temperature. So while specific humidity, it's the absolute amount of water vapor that's present in the air. And of course, the saturation specific humidity, that is the maximum amount of water vapor that can be present, as changes with altitude, of course, right? So for instance, as we go higher and higher, what we have is, for instance, as the temperature increases, right? Here in the x-axis, what you have is temperature. As the temperature increases, what we have is, it's actually the saturation specific humidity, that's the maximum amount of water vapor that can be present, is actually increases, right? So there is this clear relationship between temperature. So temperature is an important variable, controls in a way the absolute amount of water vapor that's going to be present in the air. Also impacts, it is a one-on-one, an exponential relationship with saturation specific humidity, that is the maximum amount of water vapor that can be present, right? So when we look at the specific humidity, it's also changed with altitude, right? So look at what you see here in the map. Is I'm showing you data from 1982, mean average data of specific humidity, 1982 to 2011, centered around the US, right? So this is at 100 meters above sea level, right? What do we have at 800 meters above sea level? Well, considerably drier, right? So we're pushing it while 1,500 meters above sea level. What you see here in red is actually the specific humidity, that is the exact amount of water vapor that's present in the air decreases with altitude, right? So what about 3,000 meters above sea level? It's almost completely, the air is almost completely dry. And then at around 6,000 meters above sea level, that's everything is pretty much red. As you can see here in this scale, it's very, very dry, right? So the specific humidity changes it has a relationship with altitude, right? As we go higher, the air gets drier and drier, right? Less water vapor available as we go higher, right? What about the seasons? Of course, it also changes over the seasons, right? The specific humidity change over the season. So the amount of water available change with the season. So let's look at here. Atlanta is here. See what's happening here, for instance. Just if you want to focus on Atlanta, this is December to February, typically the winter season. Well, we still have quite a bit of water vapor available in the atmosphere, right? And then, but it gets better, right? More and more moisture is available in the spring, right? And what about the summer? Well, then the humidity is considerably higher, and the amount of water vapor we have in the summer is considerably higher. And then, of course, reverse back to the trend reverses as we go from summer to autumn, and then we're back to the winter state as well, right? Specific humidity both changes as we go higher in the altitude. Also, seasonally, we have significant change in specific humidity, right? What about relative humidity? Well, unlike a specific humidity, now relative humidity, we're comparing the amount of water vapor that can actually they can be present, and that's dependent on the current temperature. In a way, so relative humidity is the proportion of the amount of water vapor to the maximum possible amount at the current temperature, right? So relative humidity actually changes on hourly basis, right? So for instance, if you check the relative humidity today in the morning, it was much higher than the relative humidity in the afternoon. So and then relative humidity can be calculated using this formula, right? So the specific humidity divided by saturation specific humidity times 100, right? So what's saturation specific humidity? Again, we're talking about the maximum, we define saturation humidity here, the maximum amount of water vapor that can be present in the air parcel, right? So if we have those two values, we can actually calculate the relative humidity. And this is very dependent on air temperature. I'll explain in this. I've shown you this slide in the previous lecture as well. So what we have here is in the morning, as it is the air temperature is relatively colder, then the air parcels, right? The volume of the air parcel is also significantly smaller. Then what that means is that it's actually easier to fill up the air parcel during the morning times compared to the afternoon, right? While the in the afternoon, for instance, it's significantly warmer. As the temperature warms, the air parcels expand. So even if we have the same amount of water vapor available throughout the day, the relative humidity changes, because the relative humidity, unlike specific humidity, is dependent on temperature. All right, so these are trends, for instance, typical trends we see. Temperature change, of course, midnight, very low, noon is where we have typically the highest temperature, and we see the same opposite relationship between temperature and relative humidity, right? And so the relative humidity, since it's actually controlled by temperature, right? Even if we have, for instance, we know that Montreal, for instance, is extremely cold and very dry air is present, well, the relative humidity can be higher, actually, right? Because relative humidity doesn't tell us the exact amount of water vapor that's present in the air, while absolute humidity or specific humidity does, right? So for instance, if you look at the specific humidity numbers here, it's 0.7, typically fluctuates between during the winter seasons. In Montreal, very, very cold, fluctuates between 0.5 to 0.7. And then in Atlanta, typically we have like specific humidity numbers ranging in the high single digits, right? And then, but relative humidity, remember, is a poor choice for comparing the amount of water vapor that's present in the air, especially if we want to compare whether a city or a location is humid or not. We can't use the relative humidity as a metrics. What we can do is we look at the specific humidity and then compare whether like the places significantly wetter during the winter season or summer season, right? So if I give you the specific humidity values and also saturation specific humidity, then it is easy to calculate the relative humidity in percentages. That is specific humidity divided by this, the saturation specific humidity times 100%, times 100, and then that's expressed in percentages. So for this question, the answer would be 100. Okay. So what about dew point temperature? A very, very important piece of the hydrological cycle. And so dew point temperature, what we call dew point temperature, is the temperature at which saturation occurs, right? What did we say about saturation? Now we're talking about the maximum amount of the maximum amount of water vapor that can be present in the air parcel, right? So after saturation, what we have is condensation, because the air parcel can't hold any more, can't hold more water vapor, right? So we have what we call dew formation, right? So a very important concept. So, but even dew point temperatures can actually change even if the air temperature remains the same. So for instance, I'm giving you two examples here, like two dates, random dates, and then comparing here in Atlanta. Well, the air temperature was exactly the same, and it was 19.4 degrees Celsius in both days, but the dew point temperature is considerably different. The reason why is that for dew point temperature, we're talking about temperature at which saturation occurs, right? So we're also talking about temperature at which air can no longer hold all of the water vapor that's available, right? So it depends on the availability of water vapor, right? So even if the air temperature is similar on a daily basis, it doesn't mean the dew point temperature would be the same, but it also depends the amount of water vapor available in the atmosphere, right? What about condensation? Again, very, very important, a key element of the hydrological cycle, refers to the phase change of the water vapor, refers to a phase change where we have water vapor changing to its liquid state, right? And then for it requires the saturation, because the air parcel will try to hold as much water vapor as it can, right? But after that point, it can no longer hold the water vapor, and the water vapor has to change its phase. And then it typically in the atmosphere, especially for instance in relatively colder regions, we need what we call this condensation and nuclei, right? So the condensation nuclei is needed because it really needs a surface where the water can form, right? So for instance, we do have this, of course, constant cycle where we have water in the ocean through evaporation is transported to the atmosphere, and then we have a condensation occurring. But sometimes, of course, we have a direct transition of a solid phase to its gaseous water vapor form from ice directly converted to its gaseous form, and then also what we call deposition, where water vapor is deposited to directly into the ice, right? So we have these 3 cycles, but more common is these 2, right? Liquid converting, freezing, and then becoming a solid, but most importantly, evaporation and condensation. But when we're talking about condensation, of course, the condensation nuclei is very important, right? The surface is very important for a liquid to form, right? Once a saturation is reached, right? So what we call dew is very common to see, especially in the early mornings, a liquid condensation occurring on a surface, right? On liquid condensation occurring on a surface, right? In this case, typically in plants leaves, you see that. So for it to happen, and we need to reach that saturation state where the air can no longer hold water vapor, and the water vapor converts to condenses to form, and then to form these tiny water droplets. So, and then of course the cool surfaces also results in lowering the temperature. Why is it important to lower the temperature? Because as long as the temperature is relatively low, then it's much easier to fill the air parcel with water vapor, right? And then, of course, water vapor can also directly convert into ice if the temperatures are significantly lower, right? And in a way, both frost and dew are pretty much the same, right? What about fog? Well, what we call fog is water vapor suspended in the air near the Earth's surface, right? And then it really occurs mostly from air cooling to its dew point temperature, right? That's the temperature at which saturation occurs, right? What is saturation? Again, that is the maximum amount of water vapor that can be present in an air parcel, right? Beyond that point, condensation occurs, right? And then what we call condensation nuclei is like a surface for it. For instance, if you have this tiny ices, right? So the those tiny water droplets can grow into the surface, right? The condensation nuclei is typically in the form of in the higher altitude in the form of ice crystals, as I'll explain in the next slides. But it could be like any form of a tiny solid surface that can serve to as a body to hold that additional water vapor. So there are 3 main types of fog: radiation fog, advection fog, and steam fog, right? So what we call radiation fog is a very type of fog. It forms typically overnight. That means as the air near the ground cools and stabilizes, right? Usually this is very common low-lying areas, right? And so where we have the cold air settling, right? And then stays very near the surface, usually throughout the night. But what about advection fog? This is also quite common over some coastal regions where we have typically warm, moist air moving over cooler surfaces, right? So the cooler surface can be both water or land. Sometimes, for instance, here you see in San Francisco for the ocean, so warm, moist air flowing over cold California current near San Francisco, right? This is happening over the ocean, and also, and sometimes we have this is an example from London where we have warm, moist air from the Gulf Stream flowing over cold London, right? So more warm air through the Gulf Stream, a very important part of the global thermohaline ocean circulation. We're bringing that more warm water closer to continental Europe, and then typically what happens is we have this advection fog, where we have the horizontal transport of air masses, right? Okay, so the advection fog in London is, for instance, different from the advection fog in San Francisco, because in the case of London, cold land is involved in fog formation over London, right? But the third type of fog is typically when you see this like when you're taking steam baths. So steam fog occurs when evaporation takes place into cold air lying over warmer water, right? So the for the evaporation to take place, then the water, the source, that's the primary source of the fog, has to be relatively warmer, right? So if I ask you in Atlanta, during which of the following months is steam fog most likely to occur, the answer would be October, because for instance, the water bodies are relatively warmer, while the air temperature is relatively cooling in the autumn. So it's much more realistic to expect steam fogs forming in October than any other months throughout the year, right? Okay, what about clouds? Well, clouds are also very important examples of condensation processes, right? So clouds, well, it's more complex because that's why we have different shapes and different forms of clouds, right? And what I mean by adiabatic cooling here is, well, of course, it's actually simply put, as we go up throughout the altitude, there is the temperature change to constant rate, right? So that's also very important for cloud formation, because depending on the amount of water vapor available in the air, we can actually and then of course the adiabatic cooling can govern what type of clouds to form at a given location, right? So there are the most common types of clouds are the cumulonimbus, where we have, like, when you have this big clouds covering large areas vertically, then usually this is associated with thunderstorms, right? And then we have the high clouds, the cirrus clouds, the cirrocumulus clouds. So there is actually, and then the cumulus cloud. So this one looks like the cumulonimbus clouds, but with cumulonimbus clouds, it's actually almost always associated with heavy thunderstorms, right? So here, this beautiful picture, well, the cumulus, it's a cumulus cloud. Well, depending on the amount of water vapor available, well, this can turn into cumulonimbus clouds. This also looks like a sunny day, so this is typically cumulus clouds. But during the winter season here in Atlanta, when we have blue skies, of course, that means as the cirrostratus or the cirrus clouds are much more common. But and also, of course, during the rainy days, the stratus clouds, both the nimbostratus and stratus clouds are common. And then sometimes, some days during the summer, of course, we have the cumulonimbus clouds as well, right? Okay. Now back to these clouds are very important, but much more important is precipitation, right? So precipitation, there are fundamentally different and important two precipitation processes. One is the collision coalescence process, and then the other is the Bergeron process. Well, the reaming or accretion is somewhere in between, but these two are the most important precipitation forming processes. So how are they different? Well, as you can see from, as you can understand from the name here, collision coalescence processes, there are, we're talking about the collision and coalescence processes taking place in the atmosphere. What happens is that, well, we have no ice crystals, no condensation nuclei for the water vapor to stick to. So what happens instead is the tiny water droplets, they collide and coalesce, and then they form bigger rain droplets, right? When the rain droplets are big enough, then they fall to the ground, right? This is the exact processes that we have. So we don't really have ice crystals where these water droplets can stick to, but what we have is this water droplets, different small water droplets colliding and coalescing with each other and forming larger water droplets, right? So typically, then when you don't need to remember this, but typically when the typical raindrops have about 2 millimeters in diameter, right? So for the collision coalescence process to occur, there are of course different two main preconditions. One, well, most importantly, we don't really have ice crystals. So that means it's not that cold, right? It's not that cold. So typically you would expect collision coalescence process taking place near the tropics and then relatively warm places, right? And well, and then if it's like in places like Atlanta where we have seasons, you would expect collision coalescence processes taking place during the summer rather than the winter, right? And while the Bergeron process is fundamentally different because it actually involves ice crystals, right? So the initial process refers to the initial process by which ice crystals grow. So it's not the water droplets growing now, but when we're talking about Bergeron process, it is actually the ice crystals growing, right? So it actually, what happens is you have the ice crystals and then you have the water droplets. What happens is that the water droplets stick with the ice crystals, and then the ice crystals ends up growing, right? It becomes, and then once it is heavier, right? Once it is heavy enough, then it can't really stay in the atmosphere, and then it really needs to come to the surface. While the what we call the ribbing and aggregation is actually somewhere in between, where we have the ice crystals getting large and also falls through the clouds and collide with droplets and then other ice crystals, right? So in a way, it's somewhere between the Bergeron process and the collision and coalescence process, and involves two processes. One is rimming, well, as you can understand from the name, and this refers to a liquid, refers to condition where liquid water freezes to ice crystals, and then allows the falling ice crystals to collide with the super cool droplets that freezes on the ice crystals, right? And then the aggregation is simply the joining of the two ice crystals. But typically, we have the Bergeron process and the collision coalescence process. So if I ask you, what's the role of the ice crystals in the Bergeron process? It's simply the to serve as surface, but most importantly, they grow from water vapor being deposited on them, right? So no collision, and they don't really provide water for the growth of the super cold water droplets. And well, again, the collision coalescence is not that relevant in the Bergeron process, while what happens is that the ice crystals, they grow from the water vapor being deposited on them, right? And of course, and depending on where we're looking at, where we are best, we also have, like, we can expect snow, rain, freezing rain, or hailstorms, right? But there is a reason why we don't typically have snows, snow forming in Atlanta, right? We don't really have days like this in Atlanta. One of the main reasons is that because for snow to form, what happens is that there is actually the temperature profile looks like this, right? So what we have is, well, we have the snowflakes forming higher in the atmosphere, but they can actually, the temperature profile, temperature change, but it doesn't really cross the zero degree Celsius mark at the surface, right? So there is no opportunity for the snowflakes to melt while they are moving from the clouds close to the surface, because it is still at 0 degrees Celsius or below the freezing point at the surface. So this condition is typically not the case here in Atlanta, while surface temperatures rarely transition to the below freezing line. So what we have in Atlanta is in the state so much rain, right? So because surface temperatures are usually typically above 0 degrees Celsius. So even if we have snow forms at higher altitude, what happens is that, well, once it reaches a certain point, well, it's not cold enough for it to stay in its solid form. So what happens is we have a rain formation. But we can also have what we call the freezing rain, right? Sometimes this happens because when there is relatively warm air present at some point through the transition, through this vertical transition, but the surface temperatures are significantly colder. So what happens is the snow converts into rain, and then within the lower portion of the atmosphere, it freezes again, and then we have what we call freezing rain. And so for a formation of sleet or freezing rain, so typically what happens is, so we have the advection of warm air, and then interrupting the vertical flow of a snow to the vertical transition of a snow to rain, right? So typically, if we don't really have an interruption, so typically what we'd have is whether if it is surface temperature is below 0 degrees Celsius, we would have a snow, while if it is above 0 degrees Celsius, what would happen is, like, we would have normal rains, right? So these are also very common in very cold regions, but where we have occasional interruption or of warm air, advection of warm air, whether it is from the ocean or from other places, typically from the ocean, where we have occasional interruption of that occurs, but it's not very common in Atlanta, right? So, but what we have in Atlanta is a typical rain formation, while the surface temperature, even if during cold days, they're not below that. They don't really transition to that below freezing point, so they stay. We have rain formations as well. But when we do sometimes, when it crosses that point, we have what we call black ice formation. Of course, and then. When we talk about what the environmental lapse rate is, the rate of decrease in temperature. So temperature decreases with altitude, typically decreases with altitude, but for a sleet formation, we actually requires an inverted lapse rate. What does that mean? So really requires this inversion, right? So there is, sleeze is like snow converting to liquid first and then back again to ice because there was an interruption. Remember, so for a sleet for a sleet to occur, we need an inverted lapse rate where we have, at some point, we have an increase in temperature with altitude instead of a decrease of temperature with altitude, right? What about hailstorms? Well, these are also not very common here in Atlanta. There is a reason. These hailstorms are typically associated with this thunderstorms, very, very common in monsoon regions and in Africa and Asia. What happens is because we have this cumulonimbus clouds covering large areas vertically, right? So we have this very complex movements of water droplets, right? So for the hail formation, we don't really have, it doesn't really give it like a lot of time for the hail to melt away. So instead, what we have is the updrafts. Once these the snowballs are formed, they don't really have enough time to melt. So what we have is like they actually come down as hailstorms, right? And then they typically they, of course, this is typically very common to occur during warm days, and then once they reach the surface, of course, within hours, they completely melt away, right? So if I ask you what precipitation process is least likely to occur in the upper portion of the high altitude clouds at any latitude during any season, remember the key point here is high altitude clouds, right? What happens at high altitude clouds? Temperatures are extremely cold, right? Very, very, very cold temperatures. So it is more likely for Bergeron process to take place because that actually facilitates the formation of ice crystals, right? That would be it for today. Next lecture, we on Monday, will be about the atmospheric temperatures, and then the atmospheric temperatures and the global temperatures. I mean, sorry about that. And attendance quizzes for the week will be posted. So I would only cover two or three questions, but today's lecture and the previous lecture, which was a brief introduction of weather, that was posted on Monday. Again, if you have any questions or trouble accessing the materials, or and if you need more time to complete the attendance quizzes, please feel free to reach out to me. But remember, attendance quizzes normally will be open until midnight Sunday, right? Have a good one, everyone.
I'm gonna say, you know what?